So this is going to be our talk on the design or data-oriented design. So we're going to go over a couple of topics here. So I am Sean Middleditch. Most of you here probably know me. DigiPen Senior, the RTIS program, president of the Game Engine Architecture Club, and I am a total nerd for engine architecture. So this talk is going to be about data-oriented design. We're specifically going to go over what exactly data-oriented design is, why it's important, what it's used for, ways to apply it to your own game projects, and then some examples of existing game engines that have made use of this and other ways you can make use of data-oriented design. Right. So what is data-oriented design? Data-oriented design, there's a lot of different ways of doing programming architectures. There's a lot of different programming methodologies. Some of these include object-oriented programming, which most of us are familiar with. There's functional programming, which is popular in certain segments, not so much in the games industry, but is really popular in a lot of communications and other algorithmic types of situations. Machine learning and machine AI is particularly a common place to see functional programming. Procedural programming is your classic C-style programming. There's a couple other popular ways of designing software, the approach you use to design the software. Data-oriented design is one of these approaches. So to give you a little bit of an idea as to what data-oriented design is good for in contrast to object-oriented programming, let's go over some of the points of what object-oriented programming is really all about. So object-oriented programming focuses on interfaces and the way that different objects interact with each other in the system. It's about abstraction, encapsulation, ensuring that you have these components that can work together and work independently. It's really a great way of doing flexible design for your software. So data-oriented design, on the other hand, is a focus on the data itself. Rather than thinking about the interfaces, how data is going to be used, how data is going to interact with other parts of the system, it's about how do you actually design your data structures for the maximum amount of use, or the maximum amount of efficiency and the easiest reuse, essentially. So some of the key concepts for data-oriented design are controlling your memory access patterns and focusing on a simplistic approach to your algorithms and removing data dependencies. And we'll go into what all those mean in a little bit more detail here. So data-oriented design focuses on making tightly packed contiguous chunks of memory for data structures. So essentially what this means is that if you've got game objects in memory, for instance, instead of creating tons of little objects to represent your game object, you've got all your different components and all these different little bits of pieces of data, and they're all wrapped behind this generic interface, these virtual function calls and these interface classes and all that kind of stuff. We're instead going to focus on a nice simple struct for each piece of your data. You're going to have a data structure just for physics, a data structure just for graphics. This data structure does nothing but handles the actual data itself. If this sounds a lot like components, this actually plays in very, very well to a general component-based design. So the data-oriented design is going to focus on the algorithms and how you manipulate that data, rather than the interfaces for interacting with that data. So if you have your physics engine, for instance, you know the particular pieces of data you need for your physics to work. You know you're going to need your velocity, your acceleration, your mass, position data. You can pack all these together in one simple structure and then have an algorithm that will just operate on physics and nothing else. So you're not mixing and matching different pieces of your engine at the same time. We'll go into a bit more on why that's important pretty shortly here. But the key point here is that the data-oriented design will maximize efficiency, and it also helps keep your code simpler in certain respects. So data-oriented design focuses on what we call plain old data. And this goes back to just a simple C struct. This doesn't have methods, it doesn't have logic, it has no behavior attached to it. All it is a container of nothing but data. Specifically, if you have a struct, this is a struct without smart pointers or without other classes internally that themselves are complex. You've got a struct that has integers and floats, basic pointers, although we tend to avoid those where possible in data-oriented programming. Just the raw stuff that the CPU can work with very, very, very efficiently. So a lot of C programming actually is kind of natively in a almost data-oriented design matter without really intentionally going that route. But all of your methods and logic are external to the types. So if we have a physics component, we then have a totally separate physics system that actually operates on these components. If we have a data structure like we want to make our own custom sorted priority queue, then we would have the data structure that holds that data, and then we would have a completely separate set of methods and logic somewhere else in the program that actually manipulates these. They're not combined together in a single class. So just a quick example we're talking about. Your traditional object-oriented programming that most of you are probably using. We create a class, for example, foo. We have some data members, and then we've got a bunch of methods that interact with these. In some cases, there are these simple accessor methods, the get and set data, that don't even really do anything besides setting and retrieving the data. If we're going with a data-oriented design style, we're using almost a straight up C-style approach. We've got just a plain struct, it's got its data, and that's it. We are done with the data. There's no methods, no logic, nothing special here. And then we have some functions sitting around somewhere else that actually manipulate this data. So you can see in terms of actually writing your code for data-oriented design in terms of how your code looks, it's really not hugely different. It's just a slight reorganization and moving a little bit back towards C. The actual strength of data-oriented design comes in how you use these structures and what you do with them, of course. So data-oriented design stresses the removal of data dependencies. This is another key part of data-oriented design. And this goes back to our component system. In a lot of modern component-based engines, especially a lot of games I've seen using Unity, which makes it really easy to do this, you have these individual components that all kind of reference each other. So you've got a logic component that's bound tightly to your physics component, which is bound tightly to a collision component, which is bound tightly to your transform component. In order to actually use any one component, you have to pull in all these other components. So this kind of data dependency creates a lot of problems when it comes to efficiency. If you want to update your physics component, you first have to go dereference the pointer to your collision component and pull the data out of that. And that's going to in turn require you to dereference a pointer to a transform component, go somewhere else, grab the data out of that component. So in order to just update just your physics, you've now gone and dereferenced and accessed 3, possibly 4 different objects. And this can cause a huge problem for performance. So one of the things here is in data-oriented design, we focus on trying to put as much data as possible in a component that is relevant to what that component needs. If physics needs some data for its position and velocity, the physics component itself contains those. They're not split off somewhere else. And by nature, we then avoid, not completely eliminate, but we'd avoid pointers and references between our data structures as much as we possibly can. One of the other advantages of this, besides just speed, is it makes it a lot easier to multi-thread your program. If you know that all of your physics structures don't reference other objects, and you can write a thread that operates on just your physics structures, while another thread is operating on your graphics data structures, and there's no chance they're going to step on each other's toes because they're completely independent from each other. In practice, particularly in games, this is kind of hard to pull off. A lot of components need to transform, need a position. Actually keeping that separate is not necessarily trivial, but there are some tricks you can do. Copying your position into physics, and then copying it back out after physics is done updating is one example of what you can do there. All right. So I said a few times now that data-oriented design is really helpful for performance. The multi-threading aspect is one particular way that it's helpful with performance, but there's some fundamental ways with how your computer works and how modern CPUs or how modern code interact with modern CPUs that make data-oriented design really, really useful if you're trying to squeeze out the last bit of performance in your game. So let's step back to the object-oriented programming approach that most of us are using. And you take your average naive game object system, which for students is going to be most of ours. That's where we start out. So we create a game object and a bunch of components, and we allocate all these objects with new. So we say new game object, and then inside of that's a list of components we want to create, and we just call new on each of the components, and we've created all these objects and put them together. Because we're calling new, each of these objects gets allocated somewhere in memory using the default memory allocator. In short, this means your objects are kind of spread out all over memory. You created your game object here, and your physics component might be spread over there in memory, and then another game object created, its physics component ended up somewhere over there in memory. Totally separate places. They're not close to each other at all. Furthermore, the update logic is also kind of strewn about. So the average way the average game engine, component-based game engine works is you have an update method on your game object. And every run through the main loop, you iterate over all your game objects and call update on that game object. And then the game object iterates over all of its components and calls update on those components. So what happens is you're ping-ponging back and forth between these different systems in your engine. So your first game object is updated, and it updates physics and AI and then graphics. And then it goes to the next game object and goes back to physics and updates that. Then goes back to AI and updates that. Instead of doing all of the physics at once or all the AI at once. So we're bouncing over the place. We've got objects spread throughout memory we're constantly jumping between in order to do our updates. And we've got different functions and code that's spread out in memory that we're bouncing back and forth between, which causes performance problems. So the performance issues come down to the way modern CPUs work. And it's actually kind of funny, because I still, every now and again, see people talk about performance tricks that don't actually work on a modern CPU. They're actually performance pessimizations. Certain things like pre-calculating large buffers of data. It's actually slower to access this buffer of data in some cases than to recalculate the data on the fly. And this ties into why having our objects spread over memory is bad. So modern CPUs have a deep pipeline. It's kind of like an automobile factory, or if you're familiar with the graphics pipeline, same general concept. A pipeline stall is whenever the pipeline is partially empty. So for example, if we have 5 stages to a pipeline and there's nothing in that pipeline because we're waiting for one thing to finish and we can't put the next item in until that first one finishes, that pipeline's going to be empty before we continue on. This is called a pipeline stall, and this hurts performance-wise. Got a couple. So the pipeline stalls occur when one instruction must wait for a previous one to complete. This is mostly dealt with compiler, but not in the case of branches. So branches are when you have an if condition or also when you have a virtual function call. So let's consider we've got all these components we're calling. We're doing an update loop on all of our components. And they're just a virtual component interface that has an update method. So we call update on component interface I component, and it's going to get dispatched to the proper update method for the specific component that you're calling into. The CPU has no idea where that's going to get bounced to, so it can't pre-cache that jump, and there's going to be a pipeline stall. The CPU is saying, well, I don't know what function I'm going to start running, so I've got to actually wait for that jump execution, that function call, to completely exit the pipeline, and then I jump to the function, and then I can start reading the instructions from that function. So you get this huge overhead for calling these virtual functions that can actually really hurt if you're calling a lot of these in a row or in a sequence. So exactly what a pipeline kind of sort of looks like. This isn't a real CPU pipeline. This is kind of a virtual made-up one. But these are kind of the broad steps. If you've got a list of instructions that your program is compiled into, the CPU is going to fetch the instruction, decode it to figure out what it is. It's going to figure out when it can when it can execute the instruction. It's going to dispatch it to the actual execution units. It's going to read that. It's going to execute it. And then finally, it's going to write back the result. And just an idea of real CPUs. The current Intel cores have about 14 stages. The Bulldozer has 16 to 19. And then Pentium 4 had 20, which is many of you remember that Pentium 4 is not known for being a speed demon. That's one of the reasons. So when you talk about a pipeline stall, that's essentially when large portions of this pipeline are empty. In an ideal case, every single stage is going to have part of an instruction in it. It's going to be an efficient factory, pushing as many parts through as it possibly can. So let's say we've got a few examples, some instructions going through here. So we've got this blue instruction that's currently in the dispatch stage and this green instruction that's over in scheduling. Let's say that the green instruction is in some way waiting for the blue instruction to finish. So it can't actually run until the blue one is done. So we're going to step through, and the blue instruction is going through the pipeline, but the green one is stalled, and everything behind it is stalled. They're not moving, and it's still executing. The blue guy is still moving through there. Nothing's happening. Finally, the blue guy goes through the pipeline, and we've got this huge empty, three stages in our pipeline that haven't had any work done on them. That's 3 cycles of your CPU that have just been completely wasted. Finally, that instruction is done, and now the instructions continue moving forward. So again, this will happen a lot in math code, tight loops that you might have over your physics bodies, for instance. This can happen a lot if you're doing a lot of weird branching, or you have all these conditions to deal with virtual interfaces, or trying to bounce back and forth between physics and graphics. You end up with a lot of these stalls, and they start adding up. A good portion of the time your CPU is executing, it's not actually doing anything. Certain modern CPUs, like the i7, has all kinds of tricks in its bag in order to try to alleviate this problem because it's so common in your average application. Hyper-threading is one way. There's the CPU will actually reorder your instructions. If you're looking at the assembler output of your program, that's not necessarily the order the instructions will actually get run in, because the CPU has a ton of silicon, or it tries to figure out and see, well, maybe this instruction, this came in here, isn't dependent on any of the other ones, so we could have put that ahead of these guys and let it run through and filled up the pipeline a bit more. On your modern i7s, this exists, but if you're coding for, say, a phone, these features aren't necessarily there, because this kind of intelligence in the CPU eats up too much power, too much silicon space. So it's important for you to make sure that you have very efficient algorithms, and that data-oriented design plays into that by making sure you can have this nice, tight, very compact loop that loops over a single algorithm at a time, and isn't trying to bounce back and forth between algorithm A and then algorithm B and introducing all these pipeline stalls. The other big thing that data-oriented design can help alleviate is the wait state. The wait state is what happens when your CPU is needs to access some memory, and that memory is not currently in one of the CPU registers. So we like to think that RAM is fast. We've got all these super high-speed RAM sticks we buy these days. It's actually not that quick at all. There's actually faster levels of memory, but they're smaller. So if we have objects that are spread all over throughout memory because we've been using standard new, or we've got these really large objects that have all kinds of extraneous data in them, then it's going to make things run slower, because actually accessing RAM is not cheap. Your modern CPU runs way, way faster than your RAM does. Access to random memory, to your RAM, can take potentially dozens or even hundreds of CPU cycles of service. In the worst case, I believe on the average DDR3 stick these days, on an i7, it's somewhere around 180 cycles. So if you try to access something in memory and it's not already on your CPU is sitting there doing nothing for 180 cycles. Again, ignoring the fact that there's things the i7 does to try to alleviate that to a certain degree. But worst case scenario, you have just eaten up a ton of cycles that your processor is not actually doing any work. And then your performance starts suffering pretty noticeably. In larger AAA games, this can actually be one of the largest bottlenecks aside from graphics. So a couple things to understand about how the memory works and why this slowness exists. DRAM, which is the main sticks of memory we put in our computers these days, is dynamic random access memory. It's essentially made out of, or it uses capacitors internally. So there's this delay. Every time it needs to read or write data, it has to wait for a capacitor to charge or empty out. The memory also has to pause certain parts of itself occasionally because the capacitors slowly leak, and it has to go ahead and refill them, otherwise it'll start losing memory. So there's all kinds of slowdowns that happen in DRAM. We end up using it, however, because we can make really, really large banks of memory in DRAM. It's very compact. And it doesn't use a lot of power because it's using the capacitor, so a lot of times when your RAM's just kind of sitting there, it's only using power and it's being used or refreshed. Long story short, it is necessary to have these multi-gigabyte machines that don't draw too much power that we use today. It's worth noting that the RAM organizes itself into banks, rows, and what's called the row bank cache. And you can generally think of these as the different access levels to the RAM itself. There's a lot of latency with DRAM. We want to avoid hitting RAM as often as possible, essentially. There's also SRAM. So older computers, if you guys were around, say maybe 20 years ago, SRAM was our main system memory. These days, you'll generally only find it inside of your CPU cache. The thing with SRAM is that it is extremely fast compared to DRAM. It is, however, very power hungry. In order for a single bit to stay set, it requires a constant stream of power to that bit in order for it to stay the way it is. So it's more power hungry, and it's also slightly more complicated to build, so you can't fit as much of it in a single area. So you can't get a 4 gigabyte SRAM stick. You can get maybe 6 or 8 megabytes, which is what you see in a CPU cache, and stick within power envelopes. So yeah, you only see this in the CPU cache, nowhere else, but it's much faster than DRAM, which is important. So the CPU cache can be used to prefetch data. So we've got all this memory, this RAM that we said was slow. We've got the CPU cache. The point of the cache is that it is much faster to access than the RAM. So if we're looking to access a piece of data and it's in the cache, it's fast. If it's in RAM, not so fast. We can prefetch data into the cache. So let's say we've got a bunch of objects we know that we're going to update all in one go. We can tell the CPU to start reading those objects into cache, and while it's doing that, start working on the first objects that's come in. So we're doing work on objects while the CPU is streaming in more data as it goes. And this gets rid of that wait state. So instead of us reading one object and then waiting for the next object and then processing the object, we're doing this all in tandem, all in parallel. However, in order for prefetch to work, it requires that all of our data be laid out in contiguous memory. If our objects are spread out in 3 different places, we need to prefetch each of these objects individually. Worse, because of the way the data structures for these systems are usually laid out with linked lists or some kind of tree, we can't actually just read the object. In order to know where the third object is, we first have to read the first object to get its pointer to the next object, read that object in, and then grab its pointer to the next object, and now we can finally read in the third object in the list. So there's instead of one nice prefetch and we keep running, we're doing all these prefetches over and over, and each one you got to wait for the first one to be serviced. So there's just all kinds of inefficiencies in that system. If instead all of our objects are in a single array, so they're all together in memory, we can say, hey, CPU, read that whole memory, or read that array in, prefetch the whole thing while I'm processing it, or prefetch it in chunks at least that fit in cache. It's going to be way, way faster, noticeably so in some cases. So a quick idea of what this looks like. Memory access in this system goes all the way down to the CPU registers, which are instantaneous, essentially, one cycle to access these. Through up to 3 levels of CPU cache that have different levels of performance. Generally, CPU cache level 1 is very fast, but it's very small. There's maybe 64K on some CPUs. Whereas level 3 is maybe all of 8 megabytes on certain CPUs these days. Then we've got our system memory, which includes a row bank. A row bank is kind of like a CPU. It's a cache for the RAM that helps with sequential reads. So again, if we have everything in an array and we're iterating over that array, the row banks are going to make it really, really fast to keep reading from a sequential area of memory. But if we're bouncing all over memory, then the row bank isn't doing anything for us. Then lastly, at the very top is network and file system access. I'm sure you all know that accessing your disk is a lot slower than accessing RAM. That's why we try to preload and stream in data. But when you're thinking about design of an algorithm or design of a data structure or performance of your game, you need to keep this in mind. You really want to keep as much of your data down here as possible, the data that you're actively working with. Because the higher up in this hierarchy that your data is, the slower your program's going to run. The more often your program's going to be, the CPU is going to be in that wait state and just spinning its wheels, not really being able to do anything. If you've ever heard of the cache coherency or cache friendliness of an algorithm or a data structure, this is what it's talking about. How easy is it to keep that whole data structure in cache and iterate over it and update it all in one go without having to bounce back to system memory all the time? So it's a really important thing to keep in mind. So allocating with new spreads the objects all over. Iterating these means you're going to be, they're not in cache. You're not going to be, you have to re-grab them over and over again. Significant performance penalty for doing that. So try to avoid that. So if you're using the standard naive OOP model for game objects, we might have something like this. Each one of these boxes represents an individual memory allocation, essentially. So you can see they're kind of all over the place. The graphics components, they're nowhere next to each other in memory. If I want to update all the graphics components in one go, I'm going to have to access this block of memory and then that block of memory. If I'm iterating over the game objects to then iterate over the components, it's going to be iterate over game object 1, then go through its components. It's just going to be bouncing over the place, and we're going to lose all those benefits we just talked about. Yeah, so we really want to avoid this in cases where the performance matters. If we're using data-oriented design, now we're thinking about how can we put our data and our data structures together in memory? How can we structure things to be more efficient for the way CPUs work? So we're going to put all of our graphics components in a single block together. We're going to put our physics components in a single block together. So now when we say, hey, it's time to update graphics, it's time to do all of our drawing, we can just access this one block of memory, and everything we need is there. We can iterate over it, and we can prefetch. There's not going to be wait states. Everything's going to be a lot quicker, noticeably so if you have a lot of graphics objects. So there is this fantastic paper that goes over everything I just went in excruciatingly higher amounts of detail, but it is something that every last single one of you as game programmers should know. I mean, I would argue you must know this. So the article is called What Every Programmer Should Know About Memory. It's written by Mr. Drepper. You can search for it. You can find this PDF pretty easily. Absolutely, you guys need to be reading this. As soon as we're on this talk, you should go look it up and take a look through it. Right. So data-oriented design is not necessarily just about performance. It is also about simplifying certain aspects of your engine design. So when you're using object-oriented programming, we like to talk about these interfaces and abstractions and indirections in order to make things more flexible and make these reusable components. And there's this very famous quote that comes up quite a bit. All problems in computer science can be solved by another level of indirection. However, those of us who care at all about performance or who have worked in large projects are very, very much aware of the second half of this. You can't really solve the problems of too many layers of indirection by adding more indirection. And that is an actual problem, is what I'm getting at here. Too many layers of indirection can make your program more complicated. I'm sure you've all been in a case where you're trying to look at a project and you're like, well, what does this function do? And you look at it and it's calling into some data structure, and you look at that and it's got a pointer to another object, and you look at that and that's calling some method somewhere, and you follow that and that's going to some virtual interface, and you have no idea where the implementation is. And you're like, I have no idea what's going on. This system is entirely too complex. I can't fix bugs. I can't reason about its performance. This is no good. So the system might very well be extremely flexible, but it's not understandable by anyone except the person who wrote it. And even then, it's not going to be understandable by him 4 years later. So data-oriented design with its focus on plain old data will help alleviate that problem. It'll get you thinking again about more simple layers of abstractions, or removing layers of abstractions that don't strictly need to be there. So the encapsulation, abstract data types, all of these just kind of lead to these horrible sets of layers that are not comprehensible. So we focus on plain old data, it gets a lot simpler. It's worth noting we can still have abstract data types. And by that I mean we have standard vector in C++, where it's got this, this behavior. You can push and pop items to it, it grows and it resizes, but the actual contained item can be anything. You can still do that with data-oriented design. There's nothing that says you can't have a standard vector or a standard map of any plain struct or any plain piece of data. In fact, that's actually a very useful thing, and good data-oriented design will actually make heavy use of this for performance reasons. It's a lot better to have a nice, well-written, well-tested, resizable array implementation than it is to kind of ad hoc things all over the place. It'll make sure you get better performance and more finely tuned algorithms. It's worth noting that the data-oriented design can be cleaner to some people's definitions of clean. Removes a lot of the cruft that builds up. It does tend to be less flexible. If you don't have these polymorphic interfaces, these virtual functions, and these abstract layers of indirection, that means every time you want to make a change, you have to go in and actually change what the code does. So if you're focusing on the iteration of your game concept, data-oriented design can get in your way. If you want to make it easy for a designer, just pop in, create a new component, attach it to a game object. This can potentially make it a little bit harder. That said, keep in mind that you don't have to have just data-oriented design or just flexibility. You can mix and match in different parts of the engine where it makes sense. And again, be aware that when I say data-oriented design can create cleaner engines, that is a contentious term. One man's clean is another man's horribly ugly. So use it appropriately and don't get into that habit of being the guy who runs around that says data-oriented design is the cleaner way of doing things. That's going to get you in some trouble here and there. Likewise, do not be the guy who runs around saying object-oriented is the only way to go. Also, neither of these are true. The real world is not binary. Only computers do that. Mix and match as appropriate. So just to kind of help you get an idea of the difference. I cannot possibly put the actual code samples in slides. Even the short one is too much. But the guys who do BitSquid recently released their foundation library on Bitbucket. And it's really instructive if you want to understand the differences between a data-oriented design approach and a more traditional object-oriented approach. For a resizable array, the BitSquid's header, which includes implementation, is 162 lines long, as opposed to Electronic Arts game-oriented STL, where its standard vector is 1,623 lines long. That is a pretty large difference in terms of the amount of code it took to write, the amount of code they have to test, and the amount of code you have to understand if you want to go here and modify things. It's worth noting that performance-wise, these should be more or less identical. They are resizable arrays. They're doing more or less the exact same thing. But in terms of simplicity, the BitSquid Foundation array, it only has some of the basic ops. It does not have all of the STL functions like the EASTL implementation does. It only supports plain old data. So for example, when you resize the array in the BitSquid library, it just uses memmove and resizes things. It doesn't call constructors or destructors on the objects in your array. So if you have a smart pointer or a class that needs its constructor or destructor, its copy constructor run, it won't handle that. On the other hand, if you're using plain old data, it's going to be a lot faster. In theory, a well-written STL can actually optimize that the same. But for some of your more advanced data structures, it can help. And then it's also worth noting that because it is a data-oriented approach, it is not going to be compatible with a lot of the same STL patterns. There are begin and end support. You can use some of the basic iterator algorithms in the BitSquid library. But it is different. It's not going to be super compatible with the STL. So that said, it might seem in some cases like the BitSquid approach is simpler. It's much smaller code. It's a lot easier to work with. It's very easy to understand. It's very, very simple. On the other hand, it is missing a lot of features. It doesn't have safety for types that need the constructor destructor. So there is a strong case to be made that the EASTL approach will actually be more beneficial in certain use cases. It's really up to you to figure out which one is going to work better for your specific needs, your specific project. I would not encourage you or discourage you from going either approach. So I would definitely recommend Googling both of these, checking out the code, and coming to your own opinion. Particularly implement something like this yourself and kind of get an idea as to which you feel is better for your particular style and the people you're working with in the project you're on. So using data-oriented design in a game engine specifically, rather than just the abstracts. So the first thing I want you to note is that especially as student or hobby projects, your performance is not going to be solved in most cases by data-oriented design. The vast majority of performance issues I see are people using the GPU APIs incorrectly. You're going to get most of your bottlenecks in places like that. optimizing how your game objects run is going to get you very, very little net result until you start dealing with very large games with very large numbers of game objects, or you're running really complex systems. So even most AAA games don't use data-oriented design for their core game objects. There are, however, certain places where data-oriented design is extremely important, and you want to make sure you are using it. You probably have already been using it and didn't really realize it. But if you are writing your physics and a hardcore physics engine that has constraints and all that, you are almost certainly using a form of data-oriented design. Trying to make it run efficiently without that is not going to work very well. So even if you are using in a AAA game engine that isn't even using components, because they typically have an external third-party library that is internally organizing all of its objects in a very efficient manner, and the components are just kind of like this veneer over the internals of that library. For graphics, and particularly particle engines, you're dealing with possibly tens, hundreds of thousands of objects, and if you're creating an individual object for each of these and calling new on each of these, and have virtual methods to update each particle individually, that's not going to work very well. Any of you who have tried that probably have learned that already. Those of you who haven't, I don't recommend trying it. It will just be a waste of time. Go ahead and use a data-oriented approach. You're going to have this nice, tightly packed array of your particles. You're going to iterate them in a single loop that iterates over them once. It's going to be way faster. The same thing can go for culling and batching. If you keep your data structures tightly packed and without all the layers of indirection, you can handle thousands of objects very, very efficiently that you might otherwise have a lot of trouble handling. There are also parts where data-oriented design is not necessarily the best approach because it removes the flexibility that you want for game iteration. All of your game logic. Anyone who thinks that there's an architecture for game logic has not written enough games. This will always be a hairy spaghetti mess of nastiness. You want to focus on making it easy to change that nastiness rather than making it optimal. It will never, ever get there. AI, some of the lower level AI, like your pathfinding system in AI might, can actually make a lot of use of data-oriented programming, but your higher levels of AI, not quite so much. And also when you're building your tools, don't worry about the performance of them for the most part. Whip together in C# and just make it as easy to build things as possible. The only place where you probably care about optimizing your data access is if you're writing, say, a light map generator. You probably want that to be as fast as possible. Your artist will appreciate being able to generate light maps in a minute versus 4 hours. But yeah, if you're working on optimizing those things, certainly go back to data-oriented design and think about, how can we pack these things in memory tightly? How can we make it very, very efficient to iterate over our data structures? And how can we make this algorithm efficient? Same thing for large-scale batch operations. So there are some existing game engine designs out there that focus entirely on data-oriented design. One that's come to popularity fairly recently is called entity systems. There's a couple articles here. One of the original ones where I believe coined the term entity system is on this entity systems of the future of MMORPGs. And there's a very popular, I believe, Java framework called Artemis that a lot of people are using to figure out how entity systems work. So the key goal of an entity system is that a component purely has data. It is plain old data. It fits entirely within that part of data-oriented design. There's no logic at all. And the entities, or your game objects, are just an identifier. They're not some object floating around that has a bunch of pointers to other components. If you have a game object you created, you give it a unique identifier like 3. And now you can identify all of the components that belong to game object 3 by just looking up component with game object ID 3. 3 individual component managers. So then the entity system, the system part of this is that the code that updates a component is part of what's called a system. So for example, you have a physics component, you have a physics system. The physics system also manages all the components. And internally, it's just going to have an array with all of these components. It's going to have some mapping to be able to, given a particular entity ID, find the corresponding component. But that's pretty much it. Then the systems are designed to be completely separable from each other. So easy way to think of this is, for example, with physics again, you make a physics system. Whenever your game object says, I need to allocate a new physics component, it says, hey, physics system, create a component for game object number 4. It adds it to the array, adds the data, and it's there. And then every time with your game loop, you say, hey, systems, update yourselves, physics updates, graphics updates, all in one go. Possibly in parallel if you're using threading, if you're using that particular threading model. It's really simple. There's not a whole lot to it. If you look up the Artemis code, which is in Java, nice and easy to read, there's almost nothing there. It is a super, super simple design. Like most of the work they put into it is the different ways of managing a system rather than managing the components, because components are so simple. And it also can create quite a bit of speed in that regard. However, I dislike the entity system approach because it does force you to make all of your components in this data-oriented design fashion. Without the logic put in there, there's no way of saying I want to have this component that is nothing but logic. Its whole purpose is to have some virtual function calls implemented so we can differentiate between the behavior of this object versus this object. So a strict entity system to me is going to be focusing too much on the performance of things where performance doesn't matter, and removing your flexibility in the areas where your flexibility and your iteration time is really key. So what you'll find is most high-end component-based engines are going to take kind of a conservative approach. They're not going to have the naive approach where all components are allocated individually. They will use some data-oriented design in the components where it actually matters. So one of the key things is you do want to focus on data-only components. If any component that doesn't need logic, doesn't need methods implemented in it, doesn't need any virtual interfaces, don't put them there. As soon as you have them, you're now kind of tied into using this extra layer of abstraction and all those problems we went over before. Always with any component system, try to use data components as much as possible. Each component has an associated factory, which is a very similar concept to the system in an entity system. The key thing here is that the factory for a particular type of component can be overridden or changed. So we can say the factory for the physics components are going to allocate everything in this memory pool. So they're all tightly packed together. We can iterate over them, data-oriented design. For some of our other components that say we only have one or two of in the system, it just uses the standard new malloc allocator. It doesn't really matter where they're at. There's not a lot of them. And then for certain other components, maybe we allocate them using a different allocator that tries to, say, put all of the logic-based components close together in memory so that we can just iterate over all of the logics for one game object, all the logic components for one game object in one go. And just kind of have this one loop over all logic, essentially, for the game. That kind of allocator is a little bit more complex, but not overly so. So the advantage here now is that we have a semi-data-oriented design for logic that will still keep things a little bit better in terms of memory access. We've got flexibility to override things when we need it and not even worry about performance in cases where it flat out just doesn't matter. So yeah, the systems manage the updating of their own components. So only the logic components have the update is again the key part here. Your data components don't have update. There is no loop that says run through and run update on every component. That's totally unnecessary. Only components that have logic have this, which you can implement in C++ by having two types of components. You can have logic components and data components, keeping a list of just the logic components separate. So we're using data-oriented design where it makes sense, and we use more traditional object-oriented programming where that makes sense. And that way we get the benefits of both these systems without having our hands tied, being locked into one method or the other. So, and I think I mentioned this before, certain aspects of your game are probably already using a data-oriented design. Even games that have no component knowledge whatsoever, they don't use a component-based approach, can still make use of this in certain ways. So the physics systems, if you're using Havoc or something like that, it's managing all of its own objects internally, and all your component or game object does is just kind of let Havoc know that it needs to create certain objects or update certain objects. And then you just kind of tell the physics library to update its state of the world, and it's doing everything as efficiently as it possibly can. They're doing everything internally. And this is kind of an object-oriented approach here. The system is abstracted away about an interface, but internally it is using that data-oriented approach. So a couple notes, just finishing things up here. Most importantly, profile code. I've seen more than a few entity systems in particular. People have written these without really understanding what data-oriented design is, or what the purpose of it is, or what the purpose of an entity system was all supposed to be. And they actually just made these really bad entity systems that were still having objects strewn all over memory. And they had the manage part, so the system manages all the components of its right type. And they're like, this makes things easier to update. But it has none of the performance advantages at all, and they're just losing that flexibility of the UP approach with not really gaining anything. So if you're going to write code and you're thinking performance is the reason you're writing it, actually profile your code. Actually make sure what you're writing is actually faster. Run some tools that, there are tools that will check cache misses, make sure that your data is being accessed in a nice, friendly way. They can give you warnings about data structures or pieces of code that are violating some of these constraints. Actually use these. Don't just assume that just because you thought you were using a system that somebody said was performant, you're actually getting a good one. And second of all, and most importantly, keep it simple. Don't think you have to go through now and rewrite a bunch of your game engine to be data-oriented design because I said that the way you're doing your game objects was the naive approach and they're super slow. If it's not actually causing a performance problem for your game, don't worry about it. Focus on actually making a good game. Focus on more flexible code that's going to make it faster for you to build up your game, especially with the time constraints we have here at DigiPen. Use the topics we talked about today when you're noticing a performance problem. We're in some of those systems like particle engines. If you haven't written yours yet, take that into consideration when you're writing those things where it actually matters. So the rest of your engine, keep it simple, go the least amount of code possible, get things up and running, move forward, make a great game. And that is it. Do we have any questions about anything we went over?
Not knowing anything about component-based design, where would I start?
Where would you start with component-based design is the question. So we've actually had a talk here at the club earlier. First, the video's not online. I do have some slides up on that. There's also a great article called Evolve Your Hierarchy that is it was one of the original blog posts that went over what components were, why they matter, what they're all about. And then there's also a great article by an ex-gas-powered games developer, Scott Bylis, I believe is his name. I might have been incorrect. But Dungeon Siege is one of the first commercial games to actually use a component-based architecture. And he wrote this fantastic set of slides and part of a research paper and how it works, why it works. Actually goes over some of the same topics here about how to make components work with multi-threading, worry about performance, and some ideas on how to build something like that into your game engine. So I definitely recommend checking that one out. I don't remember the name of it off the top of my head, but if you search for gas-powered games, component-based design, you will probably find the paper. Any other questions? All right, thank you.